Have you ever wondered how we humans look at color? How we can extract certain colors out of the scene? For example, when you're driving through the freeway, we look at all these like orange traffic cylinders or traffic cones, and we can easily spot them. We can easily distinguish the orange from the scene around it. Without really a lot of thought what these are, we can extract them pretty much very simply. What if you had to construct a computer algorithm to do the same? How do you go about doing it? In today's demystified video, we will look at color and how we will threshold color to isolate a color from a scene which is complicated. Let's dive right in. So before we dive into thresholding color and extracting color out of a scene, let's look at what it takes to capture an image. Remember from the previous lectures, we talked about that the light from the scene is focused through a lens array. This light which is focused falls onto these pixels, and to capture color we have this thing called the Bayer pattern. The Bayer pattern is basically different color gels which lets us capture red, green and blue in this particular case separately, but it could be any color filter array and it could capture multiple different colors. Then we receive this color information through the thing called the analog front end, where physical photons of light are converted into voltage or electricity, and this gives us the raw image, which is mosaic, and it's linear with respect to the intensity of light, and it's generally 12 to 14 bits if you're using a DSLR or a new modern day mirrorless camera. Then we perform white balancing. This is like how you interpret color to add or subtract different amounts of color. For example, shade, then tungsten, then cloudy, and so on. Then we take this and we basically perform something called as demosaicing, which is basically filling in the colors where the specific pixel do not exist. For example, on the blue pixel, red and green do not exist, but we are going to interpolate it to actually make the full array possible. If this is not making much sense, please go back to the previous video where I explained Bayer patterns in a much better detail, and this would help you understand this video much better. And then we perform some denoising so that we remove artifacts which exist after doing this demosaicing procedure, and then we can perform more color transformations to make the colors look richer and nicer. And then we can do something called as tone reproduction or tone mapping, which adds contrast and sharpness to the image, which makes your image look good. And then finally, to save this image, we compress the image because 12 to 14 bits is a lot. And then we finally save the RGB color image, which is non-linear with respect to the amount of light that was hitting the sensor, and it's generally represented as 8 bits. Again, if this is not clear, please refer to the previous video on color imaging and look at how color is actually captured from there. So quickly to recap, classical cameras have a combination of a lens array, an aperture assembly, shutter button and all that stuff along with an imaging sensor. In this particular case, we have this camera in a nicely enclosed body, and we have a scene, in this case an apple tree, and we have the imaging sensor shown on the right. Let's see how a single pixel is captured. Light falling in on the apple basically goes through the lens array, gets focused onto the pixel, and then falls on the RGB pattern of the array. And this RGB pattern is then interpreted and you get one pixel which is orange in color in this case. You do this over and over again for every single pixel in the image where light comes from different viewpoints and different angles and different things in the world, and you basically obtain an image which looks like this. Notice that this image is upside down by the virtue of the way the image is captured, but the idea is that we want to essentially take this and flip it front to back so that the image is upright, and this is what is done in your camera software. So once you get this image, we want to basically say, hey, some color in this image is important and I want to pick out what that color is. And we are going to talk about how we can actually do this mathematically so that we gain an intuition of what this entails. And when you are in the real world, hopefully you have a little more appreciation towards color and how well our brains can do this so quickly. So let's go back to the example from before. We have an orange cylinder. This is a simplified traffic cylinder without any white bars. Let's say the orange is fairly simple. If as a human being and I tell you, hey, look at the orange cylinder here and like mark each pixel with a white flag if it's orange, mark each pixel with a black flag if it is not orange, something like what you would do in Minesweeper, you would get an image something like this. And pretty much across the board, different people would still do this almost the same way. And again, just to recap, this is what it looks like. And we want to essentially give the robot the superpower of doing the exact same thing. And let's dive right into it. Before we get into the details, you should ask a question. Why do we want to do color segmentation? Does it really have any real world applications? Can we not just use deep learning and throw a deep neural network at these problems and solve it and move on in our lives? The answer to that is fairly simple. A lot of scenarios you can actually detect a lot of simple things with color. For example, this is ripeness of the tomatoes as you see in the background image. We know that a ripe tomato is red in color, whereas an unripe tomato is like somewhere green to yellow. Why throw a deep neural network at this problem? We can do this with simple color methods, right? And assuming this is in an orchard where there are no other red things, this is a fairly simple method. And the idea is that this can be done with a very simple small robot instead of a really expensive bulky one, which can pose dangers to the fruit and the people around the orchard itself, right? So that's the goal here. Let's look at color in a different light, wherein we want to think of color as a tool in math. So let's represent the RGB colors we had from before from each image into something called a color cube. So I am going to represent each single pixel as this R, G and B values, which is going to be denoted by this boldface vector X. It's a 3-dimensional vector which I'm going to plot, and we are going to look at the shape when we plot a lot of pixels in this cube, right? So let's have the red, green and blue axes as shown here, and the brightness of that particular intensity is going to be as you go farther away from the origin. So when we have absence of all the colors like red, green and blue, I want you to ponder it for a second and think what color that would be. You're absolutely correct. The color would be black in color because there is its absence of light, right? What about if we had a maximum value of red, maximum value of green and maximum value of blue? In the previous example, we said it's 8 bits. So it's 255, 255, 255. What would that color look like? If you were thinking of white, you are absolutely right, because red, green and blue when combined in maximum intensity gives us white light. And this is exactly how your television creates the white color light. And what about if we had maximum amount of red, no green and no blue? This would be red in color. This would be the highest saturated red, right? And going further, so if we have the maximum amount of red and maximum amount of green, we would basically get yellow light. If you do this for every single pixel in all the single values, going from 0 to 255 combinations for red, green and blue, you would essentially get something called the RGB color cube, right? Which is what we were seeing here. We just saw a few samples, but if you populate it densely, this is what the color cube looked like. The question is, why is this shape a cube and not any other thing? Why is it not like a sphere? Why is it not like a cylinder? Why is it so perfectly a sphere, a cube itself? The question here is, why is this perfectly a cube? Why is it not a weird shape like a cuboid or a sphere or a cylinder or something like that? The answer is because we represented the red, green and blue colors in Cartesian coordinate system, right? In Cartesian coordinate system, because we had equal distances in red, green and blue for the maximum value, it ends up being a cube on its own. Awesome. So if we were to do the naive method of picking color, remember that here each pixel, if you look at like different values, we want to determine what orange is, right? So I can use the eyedropper tool in Windows or like Ubuntu or any operating system you're using or any Photoshop like tool. And you can say, hey, this is 1 pixel, which is what my orange color looks like. I can plot this on my RGB color thing like before. For this particular pixel, the value was 192, 118 and 35. And if you plot this, this is what it looks like. But what if I do another color picker job, because like we might not pick the same exact pixel on the cylinder itself. I might pick something like that. And the value of that pixel looks completely different from before, right? I can keep doing this again. And if you do this multiple times or ask multiple people to do it, they would probably pick different eyedropper values, right? And this is what it looks like. The problem now here is each of us picked a different pixel value where it had different RGB values. So how do we say this is orange? How do we come up to a consensus that, hey, this is what the orange color is, right? It gets pretty complicated. So let's take another example. If you do this for every single pixel in the image, we will see something like what we see on the bottom right here, right? You'll see a lot of blue pixels and you'll see a bunch of orange pixels, and it's spread out in a very non-uniform manner, right? So if I start saying, okay, like red has to be between this range, green has to be between this range, blue has to be between this range, and that's what I will call orange, this is what we would get. And this is a tool in MATLAB called the color thresholding app. You can play with this and it's like super fun. There's also like obviously like Python code which you can build in like a few lines of code to play around with this stuff. Right, if you observe, like as we like keep making the amount of colors we include smaller, you will see like more and more like orange, but also you might see like some part of the orange are also going away, right? And if we carefully tweak it, we can get it pretty well for this image, but you'll see that there are certain like parts of the gray which have also creeped in, because if we try to go even harsher, we are going to lose more values of the orange, right? Let's look at this in a little more detail. So remember that whatever we just did in the previous case, it's essentially like saying, hey, everything that is within this range is what I want to preserve, and that's my orange. Everything that is outside is basically I don't care about it, and that's going to be 0, right? In math terms, R was between 120 to 55, green was between 0 and 255, and blue was between 20 and 200, and everything outside this range, if even one of these conditions fails, it's going to be 0, and we don't care about that, right? In other words, this essentially was, we were drawing like bounding lines on each of the axes, we did the same thing for red, we did the same thing for green, and we did the same thing for blue. I want you to pause the video for a second and think about what shape this would be constructing. So remember that this is thresholding color. We are saying everything within this range is orange and everything outside this range is not orange, right? I want you to think about what shape this would actually form in our RGB color representation, where it's bounding the color orange. If you were thinking something like a cuboid, you were absolutely right, because it's the intersection of three perpendicular planes which produce three pairs of perpendicular planes which produce like each of the faces of the cuboid. Awesome. Let's fill this with the orange color, because that's what we were calling anything which is inside is orange and everything that's outside is not orange, right? Great. Awesome. So this orange color is great, and we can, anytime a pixel falls inside this cuboid, we say it's orange. Anytime it falls outside this cuboid, we say it's not orange. Life is easy, right? The question now is, why was this thresholding shape cuboid? Why was it not something different? The answer is the same as before. The reason why we got the cube for the RGB color cube, it's Cartesian coordinates. We were thresholding non-uniformly in different Cartesian coordinate system. That's why it became a cuboid. Awesome. What if I want to like instead say like the bounding volume or the surface is actually a sphere? How would I do that? So in other words, how would I get spherical thresholding? If you were thinking a change in coordinate system, you were absolutely right. And the answer is polar coordinate system, right? Instead of thresholding it with just values of R, G, and B directly, we are going to use this equation here. We are going to say like, hey, sum of R square plus G square plus B square should be less than some value rho square, right? And if it's, and it's 0, it's outside. Awesome. Again, remember that here R, G, and B values are also would have we have subtracted the mean value of the sphere where the sphere is going to be located. Great. So now let's take a step back and but the question is, what shape do we need? If you look at the shape of where we as human beings would call orange, you might draw some weird surface which looks like that, right? And if I ask you what is this shape and what mathematical function can represent the shape, you might be like, this is too complicated and we can't do this, and it's too hard, right? And you would be right in saying that this is too complicated and too hard, and it's mathematically really expensive to do this. So instead, what we can do is, instead of doing this thresholding operation in RGB like we were discussing, we can give our robot superpowers, right? We can say, hey robot, you don't have to see the world in RGB. You can do something much better than what we humans do, right? And these are called custom color spaces. For example, like if you were thresholding in RGB, this is what it looks like. If you were in thresholding in a different color space called HSV, hue, saturation and value, which we will see in a second, you might get something much more perfect, right? Notice that in the RGB color space, when we thresholded for orange, we also got these gray areas, which are not really correct, but it ended up happening that the RGB values ended up being in our cuboid or the spherical thing like we discussed before. But in the HSV color space, it's so much better, and we get the perfect cylinder. We also get the perfect reflection of the cylinder, which is beautiful, right? As Spider-Man would say, with great color spaces come great responsibility, which means that you have to take absolute care when you're designing your color space and a custom color space, because you can have unintended artifacts which could creep into your system and could cause catastrophic failures, especially if you're using this in like safety critical or mission critical applications like a self-driving car. Awesome. So let's take the raw values of RG and B, which are on the capital RG and B here, and we transform it in this way. We would be transforming the color cube like we saw before into a conical shape, right? Where it's called H, S and V. If you have ever used a color wheel in Photoshop or Paint, you'll see that like the center part is white and all around is different colors. You're essentially looking at the top view of this cone. And so that's that circle, right? As you go around the cone, you are essentially changing the hue of colors from all of the rainbow. And as you go from the center outwards radially, you're increasing the saturation of that color. Center is white, which is the least saturation. As you go out, you're increasing the saturation. As you go from the bottom of the cone to the top, you essentially are increasing the quote unquote the brightness or the value of the color, right? And you might be thinking, why is this a cone? Why is it not a cylinder? There is also HSV representations which can turn out to be a cylinder. In this particular case, it's a cone because when you drop the value to 0, all of it becomes black, right? So irrespective of the value of your hue and saturation, if you have a value of 0, it essentially will boil down to one single point, which is black, and that's the bottommost apex tip of your conical surface. And that's how we get the shape. Great. You can also take the cube and you can like distort it in every different scale, and you can rotate it, and that becomes a linear transformation of RGB to something called as YCBCR, right? YCBCR is basically the grayscale value in Y, and CB and CR are the chroma components of the blue and red respectively, right? And the equation is a simple matrix multiplication. It's a linear transformation as you see here, and Y is also called the luminance channel, and CB and CR are the chrominance in red and chrominance in blue and red respectively. So let's take a side step and understand why YCBCR is interesting and important, right? So as we were in the 1930s and 1920s, we had black and white televisions, as they're called. Essentially, as we alluded to before, technically it's not black and white. It has the full spectrum of grayscale going from 0 to 255. So essentially it's a grayscale image which is produced on this black and white TV. As we went along in the future, color televisions came along and we wanted to transmit color, right? If you just transmitted color wherein you changed the channel from grayscale to RG and B, all the older day television channels would be rendered useless, right? You would basically be throwing out like so many people's televisions, because you cannot force somebody to buy a new television because the operator decided to switch to RGB, right? And that was not really the plan. So what do you guys think happened? Like, how did we like transmit so that we could support both grayscale and the new age color televisions? The answer was in the previous slide. So the answer is we use something called as YCBCR. Remember that the Y is the luminance channel, which is the grayscale image. So you can still support your grayscale TVs. And we added two more channels called chrominance in blue and chrominance in red, which enhance the color, and the color TV itself would basically combine these colors and make it into an RGB through transformation. And that's what was used for manufacturing color channels. And the chrominance channels would look like this. Again, they are just encoding the chrominance information. Remember that you still have to combine all the three values of the luminance and the two chrominance channels to reconstruct what we were seeing before, which is the RGB color image, which looks like this. Beautiful. So we now know how to represent color, how to transform color for utilities which we might be thinking. Let's dive forward. Right? Remember that we started with the thresholding for a cuboid, and then we basically went into a sphere, and then we said that the shape is too complicated. We ideally would want to change the shape to something like much more complicated, right? What if we wanted to threshold with a single Gaussian, right? And I will hint as to why this is important in a second, but let's say we wanted to do this with a single Gaussian distribution, because Gaussian is everywhere in math. So we would want to use Gaussian because it has nice, beautiful mathematical properties where it renders itself to amazing optimization problems, right? So what is the shape of the Gaussian distribution that would look like here if you are thresholding with a Gaussian distribution? The way we would do it is we would take all the orange values, we would basically find the mean, we would find the standard deviation, and the mean and the standard deviation together represents some shape in 3D, and anything which falls out beyond a certain probability distribution, we will say that's not orange. Anything which is higher than some confidence is going to be orange. I'm asking you, what does that enclosing shape look like? If you have ever looked at a textbook example of how a Gaussian distribution is drawn in 2D, you would have the answer in 3D. Just extrapolate that. And if you were thinking of an ellipsoid or a three-dimensional ellipse-like structure, the answer is perfectly right. Again, the way this ellipse is oriented is going to be dependent upon our standard deviation itself, and where it is going to be in space is going to be dependent on our mean. I have another video coming up on Gaussian distributions and its beautiful properties. Watch out for that. But for now, just take that we have an ellipsoid which is oriented in 3D space, right? And this is great. And remember that like this is what we got with the best of RGB. And with HSV, we got much better results, right? From here on, I want you to take this idea so that we can change the shape of the thresholding, either by changing the shape of the color space itself, or which is like transformation to different color spaces, or we can change the shape of the way we threshold, right? Either of them will give you amazing results. And for this example, like if you look at the bottom on the HSV, this is linear thresholding, but if you fit a Gaussian, this would perfectly fit a Gaussian distribution because the colors are beautifully can be encapsulated into an ellipse. So I just want you to be able to answer these questions. Why do you need color thresholding? How is color thresholding done in RGB? What do shapes have to do with color thresholding? And how do we construct various color spaces? Right? See you next time. Thank you. Bye.